Many of us can code to some capacity, whether you are completely self-taught, whether you have went for, a one-day crash course or a boot camp, or whether you went for 4 years at college. At the end of the day, it all seems to be the same. It's all coding, right? So does that mean that any one of us can just go out and be a professional software developer? Surely that's too easy. And as it turns out, you're right, it's not just like that. So what sets apart a hobbyist programmer from a professional developer? The answer is software engineering. Hello and welcome back to another Random Wednesday episode. So as you would have imagined, today's episode will be about software engineering. And the reason why we're talking about this is because more often than not, if you enter, the computer science degree in a university or college, well, chances are at least some emphasis will be placed on this, and for a very good reason. So first and foremost, what is software engineering? Well, you can think of it as a standardized, structured, and thorough approach to writing code, to basically, treating the whole development process from start to finish in a standardized manner. Of course, the question is, why do we want to do things this way? Why do we want to actually formalize things if, programming is something you can do sitting at home? Well, there are a couple of reasons why. First and foremost, we have to be sure that we are building the correct product. Don't forget, now that you're working as a professional developer, you're going to have to actually deliver what the customer wants to them. So that's one very important point. Secondly, you want to ensure that you're writing code to a certain standard. Again, this is only sort of really useful in a professional environment, when you're writing code that you expect to maintain over months or years, or when you're working together in a team. Certain conventions, certain coding styles now become important. And thirdly, you want to ensure that your code meets a certain level of rigor. And what that means is it needs to be correct, it needs to be efficient, it needs to be secure. And software engineering actually defines some techniques in which you can actually boost your confidence on these things. So yeah, in the real world, software engineering is a very important skill, and that is why today we'll be taking a look at some basics of software engineering. We'll be taking a look at, what it really is, how we really go about doing it, as well as how it all fits together. Hopefully with this idea in mind, when you actually start off with your software engineering course at school, well, it makes things slightly easier for you. So yeah, that's basically the long and short of it. Let's jump into our first part. While software engineering is often, sort of mixed up with programming, really software engineering starts before any development even begins. And we start off by actually understanding what the customer wants first. Now, as a hobbyist programmer, we normally don't do this part. We just sort of jump in, write code, and hopefully, the inspiration comes to us as we are doing it. However, again, when you're developing in a professional context, you can't quite do things that way. Instead, the first thing you need to do is requirements gathering. It's interesting how much time is actually devoted to this, and it's so important because if you develop the wrong product, you've just wasted a whole bunch of time. You don't want that. You want to make sure that you've actually developed something that is useful. And here's the deal. At face value, this sounds simple, right? Sit down with your customer, ask them what they want. Except a lot of the time, they don't know what they want either. And that's why there are actually many interesting approaches to requirements gathering as well as requirements analysis that gets us to a point where we can write a piece of software that, will ensure that a customer is satisfied to a certain degree. Let's take a look at some of these techniques as well as how they can be useful. Of course, the simplest way to understand your customer's requirements is to simply get them to provide a list. However, there are many shortcomings of doing things this way. The list could be very long, and yet, because it is actually, constructed by them, non-programmers, it may not be something that is perfectly useful for you. So usually, it's for the best for you to actually go out and gather your own requirements, and here are some ways of doing so. Of course, the bulk of the methods involve, you going to them and seeing what they actually want, but there are many structured ways of doing it. Some examples include surveys, interviews, and focus groups. These are, of course, as you expect, mostly conversational in nature, But well, at least you're the one taking down the notes, you're the one conducting the entire session, so the results will certainly be more productive. Alternatively, if an existing software suite is already available, you can also observe your users actually using that. By taking note of the things they're used to as well as their pain points, you can create a better program for them. However, what's probably the most interesting of the lot is use case analysis, so let's take a look at that. Use case analysis is a very interesting way of actually expressing, what the user wants, because the approach is to actually describe a real usage scenario, and we're doing this from the point of view of the user, not from, our point of view as the coder. There generally is a pretty specific format for doing this, and most notably, what we have is a main success scenario, expressed as a series of steps. Remember that there is no jargon here, and what this means is, well, everything is sort of very intuitive, very descriptive of what the user sees on screen and how they interact with it. So what we have here is just a very, kind of contrived example for a sales system. In order to add a sale, you want to actually initiate that. Your program will require you to specify some information, namely the name and quantity. And when you do supply the information, well, the information gets stored onto the system. And that is basically, from start to finish, what's going to happen when you do this. This is your success scenario. Now, usually we extend use cases by talking about other kinds of scenarios that could possibly happen. For example, this would be an error condition. If you actually give it a quantity less than 1, how does the software react? Well, in this case, it basically gives an error and then returns back to step 2 to wait for the user to, correct their mistake. So as you can imagine, a use case could get quite long when there are multiple extensions. In addition to this, some extra information we can include are preconditions, which, are the conditions that have to be true before we can actually start with this scenario, as well as the post conditions, and that is what will happen at the end of the day. In this case, we only have a post condition for the main success scenario, but that of course is not the only outcome. For example, if the user closes the dialog box, we can have a different post condition as well. There is another way of expressing the same thing, and that is through user stories. Now, these tend to be less detailed, but they really put you in the shoes of the user, because, well, usually user stories are expressed like this, as a statement. This statement needs to contain 3 important pieces of information. Firstly, that is, who this pertains to, what they want to do, as well as why they want to do that. So this last part is something that may be missing from your use case. We do all this for the purpose of getting good requirements that we can work with. And so the next part is to actually analyze these requirements. Usually the first step will be to actually generate 2 kinds of requirements, namely functional and non-functional requirements. So let's take a look at what this means. A functional requirement basically says what we need the system to do, right? It describes a function of the system. Conversely, a non-functional requirement usually describes a characteristic. So these could be, say, a performance requirement. It doesn't actually say what the system needs to do, but instead describes something about the process during which that is done. Once you have all your requirements in order, you can then begin to build a prototype. Now, usually prototypes are non-functional. In fact, I've done prototypes that are just PowerPoint slides. The idea is you're gonna have to pitch that to your customer, to show them what things look like, how everything is laid out, how one part of the program actually links to another, and basically, this gives them a very good feel of how things are going to work at the end of the day. Of course, this is the point where you have to go back and forth, to tweak a prototype to make sure that your users' needs are actually being met. And only when this part is done, when requirements are certain, can we actually delve into serious development. Moving on to our second stage, planning. Now, to be honest, planning actually sort of runs concurrently with your requirements gathering and analysis, but the whole point of planning is that you now have to start to think about how you want to do things in your coming weeks and months. Again, this is something we tend to not do a lot, when we are just a hobbyist programmer and we are sort of doing things on an exploratory basis. However, when we're working with a large project, tens of thousands of lines of code interacting with each other, It would be good to have, say, a roadmap or a plan of some sort, so we know how the different parts actually interact with each other, as well as how we're going to approach developing them. So yeah, the planning process can be quite an in-depth process as well, and here are some of the considerations we need to go through during this part. One big aspect of planning is actually modularization, and that is how we're actually going to break down our large program into smaller parts. Here's a sample of modularization in action. Basically, we have a game and we've sort of split it out into these components. In this particular breakdown, we also have sort of the user in the equation and basically, how modules actually link up to each other. There are many ways of formally representing this idea, but the main point is thought needs to go into how things are going to be compartmentalized so that, when you build things, it's more organized. Usually during modularization, we have two huge goals, and that is to achieve high cohesion and low coupling. Here's what this means. Firstly, cohesion refers to how much the elements within a module are actually related to each other. We can think of this in terms of what the module actually does or what data it works with. High cohesion comes about when everything is strongly related. So one example I have here is a records module in which, all the functions actually involve working with the records, either retrieving them or manipulating them. And that is a highly cohesive module. One that has low cohesion is one in which the tasks don't really have anything to do with each other. Usually we have the temptation to create, say, a utilities or a tools module in which really they are just kind of grouped together because they have nowhere else to go, and that is low cohesion. Now, coupling on the other hand actually deals with how modules interact with each other. If modules are highly dependent on each other, then we can say they are highly coupled. And one good way to test this is, if we modify one module, how much effects does that have on another module? How much do we have to actually modify the other module before everything works again? In the best case, when there is no coupling at all, modifying one module does not require modifications to other modules. You can just replace it, the program still works. So that is our best case. Usually in situations of low coupling, which is the good case, two modules only pass messages to each other. They don't care about the inner workings of each other, and as a result, they're not really dependent on each other. If you swap out a different module, as long as it speaks the same language, then everything will work perfectly. So going back to our game engine example, here is a low coupling situation in which we can test if an enemy has hit the player. We start with the game engine checking the position of the player by sending a request to the player module. It complies by giving the location back. The game engine can then test against the enemy module again to see where that is. After getting the information back, it can then perform a comparison. If the two are really colliding, then the game engine sends another message to the player module, telling it to actually deduct from the health. So yeah, this is a situation in which we're just passing messages around, and so, there is very little dependence. We can easily expand the situation to have multiple players or multiple enemies, and things will still work the same. We can easily extend this situation to, a case of multiple players, even multiple enemies of different types, and everything will still work the same way. And that's the beauty of setting things up like this. High coupling, on the other hand, is when two modules are highly dependent on each other. Going back again to our game engine example, that is when, everything actually shares a game state variable. That is, we actually store our state somewhere, and everyone just talks to that state object. This creates a large amount of dependencies everywhere, and basically any modifications is going to confuse everything. So please don't do this. When we correctly achieve high cohesion and low coupling, we achieve what is known as a separation of concerns. Each module does its own thing, it doesn't care about the other modules, and this actually increases code readability as well as maintainability. If you ever need to go in and fix or upgrade something, you know to go just to that one place, and you know for sure that making changes here firstly will not break anything else, and secondly is the only place you need to modify, to be guaranteed that things are going to basically change the way you expect it to, because nowhere else in the code is handling the same task. So yeah, great advantages for actually doing things this way, especially, when you're working on a huge project or when you're working in a team. And finally, only after all this legwork is actually complete, can we actually delve into development. Now, again, this is slightly different from developing as a hobbyist because there are certain structured ways in which you actually go about with your development. For example, one very common thing in software engineering is what is known as patterns. Now, the idea is this. Generally, the same kind of problem comes up a lot. And so to make things simple, we can solve it using a more or less standardized approach. This is highly encouraged since it creates code that is more intuitive and easy to read as opposed to, some creative way in which you are trying to solve a common problem. Also, if you follow a structured pattern, you'll be more confident about its correctness because, well, again, it's a tried and tested thing. Let's take a look at a common pattern called Model View Controller, or MVC for short. The MVC pattern is particularly significant because of how it applies to basically any program. Basically any program that has, a storage or logic component that interacts with a user interface can benefit from using this pattern. So here's how it works. Essentially, we start off with a model, which as mentioned contains our data and logic. One key point to note is that this model is completely abstract. It is the low-level representation of your data, as well as the functions required to tweak them or retrieve them. However, your user cannot directly, look at this model and make any sense out of it. Instead, if you want to show your user the content, it needs to go through a view. This view knows how to actually, take the data from the model and present it in whatever way to the user. Of course, right now, everything is just one way. If the user wants to actually modify the data, chances are they need to poke at some controls. And this allows the user to either change up what they are seeing or make some modifications to the data in the backend. So yeah, this is how model, view, and controller actually links everything together. To make things more concrete, going back to our sales example, this may be how everything can be laid out. So the information held in our model are the sales records. The view for it is to actually display everything in a table. For the user to actually interact with the various features, we have a bunch of buttons in the sidebar. And basically, well, that is the controller. Having things in this manner gives us the additional advantage of substitutability. And that is perhaps if we don't like the table view, well, we can easily replace that with a chart. Notice that in doing things this way, we don't actually require any modifications to either the controller or the model. The model, the data stays exactly the same. The controller as well doesn't change. We are only changing up how we are presenting the same data. So yeah, when MVC is done correctly, substitutability is something we achieve. Similarly, perhaps the user now is an administrator and we want to give them more tools to work with. Again, all we have to do is to replace the controller. The view and the model are not affected. But now the user actually has more controls. Don't forget, of course, that now you are number one, working in a team, number two, working on a project that, may be quite huge and yet needs to be iterated upon over time. This is why one huge area of emphasis in software engineering is writing readable code. Code that you can actually go back and modify and not have to spend too much time trying to understand what you meant writing the code the first time. This is why many good practices are actually put into place, and if you follow these good practices, it can make your code easier to read. Let's take a look at some of them. One very common good practice is to avoid magic numbers, and it so happens that I have a very good real-world example to show you. Basically, I've been creating an Arduino project that involves an infrared sensor. So when you press buttons on, say, your TV remote controller, my project is actually able to pick it up, and my code can understand which button is pressed and actually, well, reacts accordingly. However, the button pressed is actually read in as some weird numerical code like this. Imagine if I just left it in my code like that. If I came back 2 months later, no way in hell am I gonna remember what all these numbers actually represent, And yeah, this basically is extremely harmful to code readability. Usually magic numbers are not quite arbitrary as this. Perhaps there are things like, the screen width and height, or maybe they are just numbers that are preset by the programmer. However, it remains that just having a number hanging out here isn't good because you don't understand what it means, and usually the workaround to this is to actually extract them to a variable. Or in this case, because I'm using C++, I can also use a macro. By assigning it to a meaningful name, this code becomes much more readable. This tells me that this is the previous button on my infrared remote control, and well, that is infinitely more readable than just having a bunch of numbers like this. So yeah, they call this magic numbers, as if the number was magically selected. Another good practice is variable naming. Now, there are actually a lot of rules for this, but the one I find the most useful is just, picking names that make sense. For example, when you have a function, you don't want to call it something like database. That really doesn't say a lot about what this function actually does. Instead, what is usually preferred for function names are actually verbs, something that implies that an action will take place. For example, query database now tells us that, okay, this function actually pokes into the database and runs a query. So it is a verb, it describes an action, and that makes things so much clearer. Similarly, for things like Boolean variables, we want to make sure that, when you look at it, you know what it means. For example, isOn actually describes a state. And this is even more useful when we use it in conjunction with if statements. If power is not a statement that makes a lot of sense, but we can basically read this one as if we were reading English because, saying if is on is very clear, right? If it's on, this is true, we do something. Apart from knowing how to code well, there are also some tools that, it will be good if you could get familiar with. And one huge example of this are revision control systems. You probably have heard of Github. Github is a place in which people upload their code through a revision control system. What these do is they help you keep track of changes, so you can easily jump back and forth between versions. At the same time, they also help you collaborate with other coders because, everybody can actually commit their code and everything gets merged together to create your final product. And finally, testing. Again, something very different from, when we actually do our own hobbyist development. Because, the way we normally test our programs is to just open it up, randomly click around, and if things work, then that's all good. But again, when it comes to software engineering, we need to be a little bit more confident than just saying, I sort of poked around in there for 5 minutes and everything seemed okay. Usually for larger scale projects, what we do is automated testing. That's right, none of that mucking around, trying to find bugs by just clicking around. Instead, you use a tool and you basically tell it what to test. So it goes through your code function by function and runs a set of test cases on each one of them. This is often known as unit testing and is quite an important part of software engineering. We've actually gone quite in depth about unit testing in an earlier video, but I will quite quickly summarize what are some of the important concepts. If you want to know more, you can always check out that video itself. What probably deserves the most emphasis is that testing is not for finding bugs, right? When we're actually, properly testing a system, what we're really doing is to check the real world, what's happening in our program against our expectations. So with that in mind, we can think about how we can actually perform testing. And most commonly, we use a technique called unit testing, which is automated in nature. Now, let's say we want to test this module. We can actually use our testing tool to basically poke at it. So for example, we can actually, test a function of it, and critically along with that, we actually give the expected results. Then we run the actual module itself, it gives us back the answer, and we can check it against our expectation. If the two things match, all is well. You know that the module is actually working the way you expect it to work. Well, not with just one test, right? If we were to actually perform a subsequent test and there is a mismatch, in other words, the test fails, then not only do we know that there is a problem in the module, we know exactly, what sort of operation it fails on, and how it violates our actual expectations. So for example, in this case, we could perhaps infer that, hey, it's actually accidentally adding the two numbers instead of performing a subtraction. So yeah, usually when we have a bunch of unit tests and we run it and some of them fail, it allows us to very quickly pinpoint the error. On top of unit testing, we also perform what is known as integration testing, and this is basically when we use automated testing to test multiple modules instead. So instead of testing one module to see if it's working correctly, we are now testing to see if multiple modules working together are still doing their job correctly. This is quite important because, well, modules can work correctly individually, but if they were linked in a way that doesn't make sense, things could still be broken at the end of the day. So it is still very important to actually test the integration between modules. Going back again to our sales example, we can actually attempt to edit a record via the controller, and then check to see if the model has changed. If it has, then it implies that this particular linkage is working correctly. So these are our testing methods. In terms of testing methodologies, there are generally two different approaches. First, there is what is known as black box testing, and that is when we treat our module as a black box. We don't care what's happening inside it. Instead, we just work with its specifications. We just supply it particular inputs, expect it to do its magic, and ignoring what it does, we just check its output and see if that meets our expectations. That's black box testing. Alternatively, we can also do what is known as white or glass box testing, where we actually care about the internal implementation. This can range from just crafting our inputs strategically so that, they actually exercise the internal implementation, to actually delving deep and testing internal use features that may not be exposed when we look at it as a black box. So yeah, two kind of opposite approaches, and both have their pros and cons as well as their values. In the best case, we want to test both ways. However, so far we're just testing our functions for correctness. There are other things we can do as well. For example, GUI testing, where we actually make sure that, everything that appears visually to the user works the way we expect. Again, the methodology is very similar because, well, what we're doing is still giving it an action and then testing the outcome against the expectation. Except now we're talking in GUI terms. So GUI testing in the real world could involve screen capture and screen reading tools, as well as some automated method to generate keystrokes on your program. Security testing is another one. While our basic methods do actually work as well, we can also use some randomized methods. For example, on a login box, we can repeatedly send random values to see, if the system holds up, if the system actually doesn't exhibit any flaw. This is important because when we are doing, our basic testing, we are feeding it values. We're actually coming up with values to test. However, when it comes to, something like security, we have to kinda expect the unexpected, to use a very cliche term, and that's why using random inputs can be quite valuable. When it comes to testing, one metric is code coverage, and that is a measure of how much code is actually being tested. As your program gets complex, your code is everywhere, it's in functions, it's in loops, it's in if statements, so getting 100% code coverage is very difficult. This is actually made worse by things like, say, loops. To really thoroughly test your program, you have to test to make sure it works correctly when a loop runs once, when it runs twice, when it runs 3 times. Basically, every possibility needs to be covered, and that is close to impossible. Similarly, if your program actually has some kind of state, you need to make sure that things are working correctly regardless of whatever state your program is in. And again, that is very difficult, especially when, programs have many possible different states. Despite that, of course, the greater code coverage you have, the better. And in fact, some programming methodologies completely surround the concept of testing. And one example of this is test-driven development, or TDD. As its name implies, TDD surrounds writing tests first. So in fact, before you actually write code, you write your test, you watch your test fail, and then you basically fix the failing test. You write just enough code to fix the test, no more, no less. To continue, you're gonna have to write another test, and basically rinse and repeat. And this is one way in which, your program can get very good coverage. And there you go. Today we've taken a look at our 4 general phases of software engineering. Now it's important to note that, even though we lay it out as sort of phase 1, phase 2, phase 3 and so on, it's not really, completely separate. A lot of the time these phases may overlap and in fact sometimes become completely concurrent. So that's an important thing to think about. Also, what we've seen here is one cycle, sort of the development process from start to finish. Except usually development doesn't really end there. When you're done with your product, your customer is happy, you deploy it. Chances are after a while they might ask you for certain improvements, certain enhancements, certain bug fixes, and basically the whole process starts again. Because again, you have to ask them what they want, go ahead and plan how to do it, prototype it, and then test it. So it's the entire cycle all over again. And for larger scale projects, this could basically go on and on continuously. Now, today I have barely scraped the surface of software engineering as a subject. Really, these are things that people go on, full university courses to learn, so there is certainly no way I can actually do this in just one video. However, hopefully what this has given you is a good overview of, the different phases as well as what are some of the considerations in general. And I think all these things are good to know, seeing as that, computers are becoming a bigger and bigger part of our lives, even in businesses, in administration, even in our personal lives. So yeah, if you ever have the interest of doing development, especially on a large scale, software engineering is definitely something you need to know. It's something that preferably you could be comfortable with. And yeah, if you have that sustained interest, definitely consider, taking a degree program in this area. When you actually, graduate with your degree, you are armed with very powerful skills, putting you in very high demand. Computers aren't going anywhere for a very long time. So yeah, good software engineering skills can bring you a very long way. Now this episode has run a little bit long, so let's go ahead and wrap things up. Thank you very much for watching. I hope you've gained some insight today. But until next time, you're watching 0612 TV with NERDfirst.net. Thank you very much for watching. If you like my work and are feeling generous, you can shoot me a one-time donation on PayPal or sign up for a recurring one on Patreon. Of course, you can simply like, comment, and subscribe. You know the deal. For more videos, links to my channel and a related playlist are on screen. Thank you for your support.